It's working now, I think. So yeah, well, together with partners from Italy, Germany, and Austria, we recently finished a research project called DRACO, Design of Railway Components. And beside others, we try to answer those two questions you see here. How do cracks behave in corrosive environment, and how do cold-rolled components behave in a corrosive environment? So let's start with the first topic, how do cracks behave in corrosive environment. To investigate this behavior, we manufactured two types of specimen, a single-edged notch bending specimen with quite big dimensions, and a CT, a compact tension specimen. In both specimens, the notch was introduced via electro discharge machining. Afterwards, to receive a really sharp notch, we use a razor blade polishing machine, own built, where we coated the razor blade with a diamond paste and draw the razor blade several times above the notch root, and finally receive a really sharp notch. Okay, afterwards, we tested we introduced a pre-crack by compression pre-cracking with a load ratio of 20. The cyclic stress intensity factor to introduce this pre-crack was always lower than 60 megapascal square meter, and we measured the length of the pre-crack via optical microscope. The general test parameters afterwards, where we apply a frequency of 95 Hertz. We performed the test at this test rig from a Rumul Testronic. The tests were done at ambient air with constant temperature and humidity, and the total initial crack length to calculate the initial stress intensity factor was the sum of the notch depth, the razor blade polishing depth, and the pre-crack. Okay, to investigate now the influence of corrosion environment, we built such a dripping device where a corrosive fluid was dripped onto the specimen above the notch. So approximately every 2 seconds, the fluid was dropped onto the notch root. Yeah, and we measured the crack length via direct current potential drop technique with a constant current of 10 amperes. And the distance of the probe tips to measure the potential drop was 3 millimeters. So that's to the measurement setup. And then we already come to the first results. We determined the long crack threshold according to the standard E647. So we performed first a test in ambient air. So it can be seen by the red dots, and receive a long crack threshold of approximately 6.8. And afterwards, we perform the same test by using this dripping device I showed you before. And you can see that we receive a significant higher threshold, the range of 7.2 megapascal square root meter. What also can be seen here that at the same stress intensity factor range, I have a significant lower crack propagation rate for the tests under corrosive environment. Good. Then we had a look on the Paris region. So we moved from the load shedding method to constant load delta K increasing method. And here the black dashed line is the crack propagation, the fitted crack propagation rate for a standard test in ambient air. And then I first want to draw your attention on the blue dots. So these tests were performed under with CT specimen. They were dived into this corrosive fluid, and we received this crack propagation curve. So significant lower as the standard test. We compare with the dashed black line. And afterwards, we performed again with the big LCB specimen, the stripping tests. And here we apply alternating 1.5 hour standard test. That means at ambient air, followed by half an hour of the stripping test. And the crack propagation moves as soon as I turn off this stripping device. Significantly, very fast drops to the crack propagation rate of these immersion tests. And as soon as I stop this stripping, the crack propagation rate increases again until it reaches the crack propagation rate of the standard tests again. So I always switch between those two boundary limits, even by ambient air and the immersion test. Okay, then we come already to the second topic, to the second question. I want to show you some results, how to control components behave in a corrosive environment. Therefore, we manufactured such a rotating bending specimen and introduced high compressive residual stresses via code rolling. You can see that this code rolling device. We afterwards measured one specimen with XRD the compressive stresses at 5 points across the specimen length, and at each point and the cross sections also 3 points along the circumferential direction. So, and you see that we receive high compressive residual stresses at all points, varying, of course, due to this parameter setup, due to this rolling device from -276 up to -615. Okay, the prepared specimen were then tested in a rotating bending machine with a test frequency of approximately 100 Hertz. We defined the run out with 10 to the power of 7 cycles and evaluate the endurance limit with the staircase method. Then here we applied this corrosion tank for spray tests. Okay, then to the results. First, we should compare the dashed lines again. So the endurance limit in air is the blue dashed line. And yeah, that's for specimen, not rolled specimen, standard specimen. Afterwards, due to the cold rolling, the red dashed line, you can see we increased the fatigue strength of approximately 15%. And then we did the same, or similar experiments with the under rainwater conditions, so in corrosive environment. Here the dots are run out points, and the crosses are failures. In blue, you can see the results for not rolled specimen in corrosive environment, and in comparison in red, the cold rolled specimen. And you can see that even under corrosive environment, I obtained the same fatigue strength as a standard specimen in air. And compared to standard specimen in corrosive environment, I increased the fatigue strength up to 40%. So time is up, or okay, just a very short. Research partners Stefano Beretta and industry partner Lucchini performed similar experiments with a real scale axle, where they introduced different notch depths across the section, across the railway axle. Yeah, and they obtained similar results. So that's just, if you're interested, is the paper from Daniele Recazzi. Yeah, okay, that's it. Only have the summary left. Okay, thank you very much.